Alright, so today we are looking at special products of polynomials, and a lot of today's lesson is taking what you already know how to do and simplifying it, making it even easier, because there are certain patterns that we can see that allow us to complete the same types of problems in maybe one step instead of three. So we're going to look at that. There are some special cases where if we remember that special case exists, we can apply a rule that allows us to find the product or the square of that very easily. So that's what we're doing. It says that there's actually a pattern when we take binomials and square them. And that pattern is, well, you just take the first term and you square it, so that's where they got the a squared. And then the two middle terms, you multiply them together and you double them. So that's plus 2ab. And then you take the last term and you square it. Same thing with subtraction. The only difference is when you're subtracting with a binomial, you just have a minus sign in the middle of it. So if you remember those special patterns for those binomials that are squared, it only takes really one step to complete them. Does that make sense? So the way I remember it is, okay, if I have something like the first case, a plus b quantity squared, or a minus b quantity squared, the only difference is I have an a squared and a b squared in both of them. I just have to remember that one of them is plus 2ab and the other one is minus 2ab. And then you have, of course, a plus and a plus. So everything's the same with the exception of the sign right in the middle there. Your book talks about the square of a binomial, like the actual square of it. These things, sometimes we wonder, why do we say something is squared? Well, back in the day, a lot of the formulas that we have now were derived from geometry. So they actually looked at concrete ways to represent what we use in algebra today. So for example, we have this literal square that looks kind of like a Punnett square, right, that you see in biology. So what they did was they said, okay, let's say I have a square that has length a plus b and length a plus b. Well, all I have to do is, to find the area, do what with those sides? Multiply them. So again, if I have one length that is a plus b and another length that is a plus b, if I find the area, all I have to do is multiply them, and when I multiply them, I get this. Does that make sense? That's why we say we square it. Any questions about that? Where things come from? Once you recognize this pattern, it makes things a lot easier. And when you take biology and you do Punnett squares, if you know this, then you don't even have to really set up the Punnett square. Okay. Moving on. Do you need more time? Okay. Okay, so we're going to take a look at two examples here. Of course, you can always do this the long way if you want, but I would encourage you to look at these patterns so that you get through things quicker. Remember, what matters with these problems is, yes, accuracy, for sure accuracy, you want to get it correct, but you also want to be able to do these quickly, because when you progress through mathematics, you'll be given binomials and trinomials in very complicated scenarios, so you want to be able to do these quickly as well. So that's one of the reasons we develop these patterns, to help us get through these faster. So 3x plus 4 squared, according to our last slide, a plus b quantity squared is a squared plus 2ab plus b squared. Therefore, based on that, I know that I take the first term and I square it, so that'll be what? Nope. Nope. 9x squared. So you both had parts of it. So 9x squared. This is your first term. Then you take the two middle terms, you multiply it and double it. So what is that going to be? 24x. And you take the last one, you square it, which will be, there you go. See how I completed that in one simple step. All right. So if you think you know what to do for the next one, go ahead and do it. All right. First term, square it, which will be what? 25x squared. Okay. So what do we have to remember about the next sign? It's minus. Minus what? 20xy. 5x times 2y is 10xy. So minus 20xy plus what? 4 y squared. Good. Yes.
For the next one, when you like show arrows from like which ones are multiplying, I'm kind of confused like how we get that.
Yeah. So for B, yeah. First step, right? A squared is taking A, B squared, right? So first term squared is 5. So you have to take the entire thing and you have to square it, right? So you have to take 5 squared and x squared. That's how you get 25x squared. And then the next thing, 2ab, is this. So A and B, A is 5x, B is 2y, right? We already know there's going to be a minus, right? So 5x times 2y is just 10xy, and then we double it. So the 2 in front, and that's how we got 20xy. B squared is this one, so we just take that second term. That second term is 2y, and we square it. So when we square 2y, you get 4y squared. Does that make more sense?
Yeah.
Okay, good. Okay, try this. We should all take one step. Alright, so let's check our answers to 1 through 4. Do you need me to go over any of those? Did you get them? It's a lot easier, huh? You know that pattern, it does make life easier. Okay, we're going to learn another shortcut. The quicker we can do things, the better. And I talked about this one yesterday too. There's a sum and difference pattern that we're going to talk about. We discussed this yesterday, and all this says is if we have the same two terms, but we have a plus and a minus for our binomial. So I have an x and I have a 3, and I have an x and I have a 3. What separates the two binomials is that I have a minus here and I have a plus here. Well, it turns out that whenever I find a product of something like that, the middle terms always cancel out. So normally we're used to saying something like this. If I have a plus and a minus, and I have those same two terms on either on both binomials, then that middle term goes away. And what I'm left with is a squared minus b squared. And the way I remember it is, if you multiply negative and a positive, you get what? a negative. So if I'm finding the product and I have a negative and a positive, I'm going to have a minus sign. Does that make sense? So in this case, it's just going to be the first one squared minus the second one squared. Does that make sense? Yeah, so if you have a same terms, so here we have a t plus 5, we have a t and we have a 5. We have a plus and a minus, so the middle terms are going to cancel, so what's the answer to that? Yep. Yes. That's a nice pattern that actually we can apply to many different things that we'll take a look at. Some simple math, too, that you might have learned in elementary school that makes life a little easier. Okay, so try that. All right, what did you get? Yep, then x squared minus y squared. Nice and easy, huh? All right. So you ready? Here we go. I never knew about this until I saw it in the book, and I thought this was really cool. They talk about doing mental math in a different way. And you might be thinking to yourself, well, what's the point? I have a calculator. True, most of us do. We have our phones. But, there is that rare occasion where something breaks down, or you just need to calculate something rather quickly, and you just don't have the tools. Yes, use the tools if you have them. But it's always good to develop what we call number sense. Number sense is being able to really understand basic operations. I remember in college, one of the biggest things that our professors told me as a mathematics major, not just me, but our entire class, was like, you guys have no number sense. You rely on your calculators, blah, blah, blah. So all of our tests, we had to do everything by hand in addition to all the theoretical math. So we were sitting there doing long division by hand. It was the worst. And it was all to develop number sense. So this is what we're going to try to do, is develop more of that number sense. It turns out that back in grade school when we did this, we multiplied 6 times 4, 2 times 8, added to 0. Remember all that? You don't have to do that. You can actually use those patterns that we just looked at by thinking of 34 in a different way, 34 and 26 in a different way. And what you want to do is think of them in terms of 30. So what I mean by that is, what do I have to add to 26 to get 30? 4. Okay. So really, 26 is 30 minus 4, right? What is 34? 30 plus 4, right? Well, look at that. I have the same two terms, right? A 30 and a 4. So really, if I want to do this rather quickly, what do you think I'm going to do? Square both of them, right? So I'm going to take 30 squared, which is just 9 and I have 2 zeros, right? And then the middle terms are going to cancel out, and I have a minus 4 squared, which is 16, right? So what's 900 minus 16? Yep. That's what that was? A lot quicker. Of course, you can use your calculators, but again, developing that number sense. My mind was blown when I read that. Any questions? Does it work on every 2 terms that you have to multiply? No. But usually the ones that you will, you'll see, oh, okay, well 26 is just 30 minus 4, 34 is just 30 plus 4. So it'll be pretty obvious, hopefully at this point, to see that. Yes?
To use the minus plus thing, do they have to be the same number?
That's a great question. And they do. They do. That's why this won't always work. Now, you can set up something like this and do distributive property, of course. You can rewrite any number as a set of 2 numbers, right? and another one is assigned you two numbers, and if you want to just do distribution properly, you can. But to use this particular pattern where it takes really one step, you have to have the same numbers. That's a great question. I'm glad you asked it. Any other questions? All right. Try 48 and 52. Okay. What two numbers did you come up with that were the same? Yep, 50 minus 2 and 50 plus 2, right? Perfect. You have 50 minus 2 and 50 plus 2. So really what you're working with is 2,500 minus 4, which is what? $2,000 what? 496. 2,496. Questions on that? I don't know. I thought that was pretty cool. We can actually apply the same logic to taking things and squaring them. So, what I mean by that is, of course, we can think of two things. Now, my trick is take things that are easy to square, because you don't want to make it harder, right? You don't want to say, well, what's 15 plus 1 times 15 plus 1? Well, in that case, you might as well just take 16 squared, do it the long way. What I ended up doing was 10 plus 6. Because I know the square of 10, which is 100, right? So we've already talked about this. If I have a plus b squared, what is that going to be? First one, square it, and then what? The two middle terms, multiply them and do what with it? Double it, plus 2ab plus b squared. So really, what you're doing here, I typed it out for you. You're just taking 10 plus 6 squared. So 10 squared is 100, right? Middle two terms multiplied together. 10 times 6 is 60, times 2 is 120. And then 6 squared is 36. So 100 plus 120 is 36 is 256. Does that make sense? Yes. On a test? I don't know yet. I don't know. Maybe. Do you have any questions about that, what I just did? Take two numbers that are easy to square and work with those instead. So 10 is easy to square, 6 is easy to square. I just take those two middle ones, multiply them together, double it. And then you're just adding things at this point. It's a lot simpler than saying 16 times 16 and then writing it out. Now, the argument could say, well, I'm used to that, so that's easier to me. Yeah, of course, because we all grew up with that, you know. But at the same time, if we learned this, I mean, think of how many steps we would have saved, you know. So it's good to know. Okay. Yes. You may. Go ahead and try these. All right. Let's see how you did on 5, 6, 7, 8. If I were to ask a test question on this, Brandon, to address your point, it would be something like number 8. Describe how to use special product patterns to find that. X squared minus 100. Did you all get that? 4x squared minus 1. X squared minus 9y squared. And then rewrite 21 squared as 20 plus 1 quantity squared. Then just take the first one, square it. The middle two terms, multiply them together, double it. and the last one and square it. So you end up with 400 plus 40 plus 1, which is 441. Does that make sense? Okay. Excellent. Do you have any questions? On number 8 especially. Simplifying Your Life, brought to you by Miss Wynn. Okay. You're a dog breeder and you want to breed 2 dogs so you can have puppies. So, we're going to look at the possibility of getting a black dog versus a gray one or a white one. So if you've seen this in biology, you set up a Punnett square like usual. Mommy and daddy, black, white, right? Set up the Punnett square, and we know that. We've seen it in biology. Now, it says, this is a pretty simple one. A says, what percent of the possible gene combinations results in black?
100%.
Yep, how'd you get that?
Because it's 1/4 and 1/4 is 0.25.
Yeah, 1/4. Show how you could use a polynomial to model the possible gene combinations of the offspring. So let's think about this. From mother, you have a 50% chance that you can get a black gene, right? 50% chance.
Or 50% is
No. You're looking at just a black gene and a white gene. Together they make the gray, right? But for mom and dad, we have 2 possible genes. You can get a black gene and a white gene, right? 50%, right? And 50%. You, or not you, but the puppy, has 50% chance of getting a black gene from mother and 50% chance of getting a white gene from mother, right? Same is true for the father, right? So what do I have to do to that? Square it. And, oh look, that looks a lot like that, right? Which looks a lot like that. Yeah? So obviously you can apply the same logic to your Punnett square, and when it's easier in biology class to do these types of problems, you can thank Miss Wynn. 0.25b squared plus 0.5bw. That's what they did. They just took the 2 middle terms, multiplied and doubled it. And then 0.25w squared. Now if you look at this, it says, show how you can use a polynomial to model the possible gene combinations of the offspring. The coefficients show 25% black, 50% gray, 25% white. So you can show, I mean, you can get that from here, of course, but you can model it with a polynomial. Does that make sense? All right, we like to model things in math. Okay, we're done. And now I gift you with homework. You're welcome.